Alright, we're back to talk about forces on a ramp. We did this last year, and it was one of the more difficult things that you did. This year, forces on a ramp, not only because you're going to get a lot more practice with it, but also because you know a lot more physics now, you understand how things are supposed to work. This isn't going to be too bad. That being said, the problems will get harder, but you're more equipped to deal with them now. One of the things you might remember from last year is that the most important thing to do when you're dealing with an object on a ramp is to tilt your axes. You tilt your axes to align with the object's motion. And as a consequence, what happens, and makes this a little tricky, is the normal distinctions of sine telling you the y component and cosine telling you the x component switch. And we'll see why that happens in just a minute. So, a very simple example to start off. A box is placed at rest on a ramp as shown below. The ramp surface is frictionless. First step, draw a free body diagram for the box and write the net force equation. So, let's start with our free body diagram. We're going to make a dot. We're going to label it box. And the next step is to draw an axis. Now imagine if I had made an axis that looked like this. You know, your standard, fairly standard X and Y. This is a box that's on a ramp. There is no friction on the ramp surface. So obviously the box is going to slide down the ramp, okay, in this direction. Now what direction is that? If I use this axis, then the box is moving not only in the positive X direction, but also in the negative Y direction. That's two different sets of equations that I'm going to have to pay attention to. I'm going to get accelerations in both the positive X direction and negative Y direction. And that just seems like a lot to deal with, okay? That's not a good idea. Instead, what I want to do is tilt the axis to align with the motion of the object. The object is going to move in this direction, so one of my axes, or one of my positive directions, should be in that direction as well. So what I have now is X and Y like this. Now I say that the box is only moving in the positive X direction. The positive Y direction is perpendicular to the ramp surface, and this box is very clearly not about to just blast off the ramp or sink down into the ramp in this direction. Now what I've done is I have restricted the box. I haven't changed anything physically, but based on my system that I've set up, my axis, I now have the box only moving in one direction, which is what we want. Okay, that's good. So I've got my axis. Now what I want to do is put the forces on there. I know that since this is on a ramp, there is a normal force, and that points perpendicular to the ramp surface, so that would be in the positive Y direction. And I know that there's also a force of gravity, which points straight down. It is not exactly opposite the normal force. The force of gravity pulls things straight down towards the center of the Earth. That would be in this direction. So I kind of just gave this away a little bit. The normal force is in the positive Y direction. How could we describe, that should be a G, I apologize, how could we describe the force of gravity? If you tilt your head and look at it, you can see that there's a component of this force in the positive X direction, but also a component in the negative Y direction. And that's fine. It doesn't, that's okay. Having the motion in one direction is what we really want. If there's a force that is in, that originally, before we split it up into components, is not in either direction, that's fine. We just need to make sure that the motion was in one direction so we could eventually get one acceleration. We know how to deal with this. We know that this has to be split into components. Our components will be one in the negative Y direction and the other in the positive X direction. Now, the tricky thing here is figuring out, okay, well, where's the angle go? Okay, because I need an angle so that I can name these components. And in order to figure out the angle, what we're going to do is go back up to this drawing, and I'll show you how we can determine that angle. I'm going to draw a line straight down from right under the box. Okay? And notice what this has done is I have made a smaller, similar right triangle out of this whole ramp. And since it's a right triangle, I have a vertical line intersecting a horizontal line. I know that that must be a right angle right there. Now remember how the angles of a right triangle work. They should sum to 180. So if I want to know what this angle is right here, I know that 180 must be equal to theta, this angle, plus 90 degrees, this angle, equals this. I'm just going to call it x for right now. I subtract 90 and theta to the other side. 180 minus 90 is 90 minus theta. Okay, and I understand, I get now that this angle must be 90 minus theta. Now, does that directly help us with our free body diagram? No, not yet, because we want to know where theta goes, not where 90 minus theta goes, okay? And you might say, well, doesn't that mean that 90 minus theta is equal to some other angle? Well, no, not exactly. Does it mean that it's equal to this? No. The only way that these two angles would be equal is if theta was 45. Then you'll get 45, 45, and 90. But that's not the case most of the time. Okay, so as you can see, this angle right here between a vertical line and the ramp surface is very similar, and in fact is similar or congruent to this angle right here. This component is parallel, to the ramp surface, and this force, the force of gravity right here, is a vertical line. That means this angle right here is 90 minus theta. Again, that's not really useful to us. We want to know where in this diagram theta appears. Obviously, it's going to be here, but let's see why that is. I'm going to draw in a dotted line now, and that dotted line is going to be perpendicular to our ramp surface, like this. And if that dotted line is perpendicular to our ramp surface, that means that this whole angle from the ramp surface to this perpendicular line must be 90 degrees. Which means, if this is 90 minus theta, how much is this right here? Again, I'm going to call this x. 90 minus theta plus x must be equal to 90 degrees. If I subtract the 90 over to this side, I get 0. If I add a theta over to the other side, I see that this angle right here is now theta. And by inspection, we see that this angle here is congruent to this angle right here. So this must be theta, right there. On your free body diagram, if there are angles involved, you do need to show where that angle goes. So, the reason we want to know where theta is so we can label our components and see which one is which one has the cosine attached to it, which one has the sine attached to it. Now, you might say, well, I don't really see a triangle here. Imagine if I took this component right here and just moved it down here. I would therefore have two components that are perpendicular to one another, therefore there's a right angle, therefore there is a right triangle for us to use trig here. I don't even have to go that far though, because I know that any component that is directly next to the angle is the one that gets cosine on it. So this component right here must be FG times cosine of theta. This one up here must be FG times the sine of theta. Okay? So, remember I said at the beginning, cosine and sine switch. Take a look at the direction of the FG cosine term. That's the negative y direction. Likewise, the FG... Is that a G? Yeah. Oof. Oh, okay. I see what I did. The FG sine theta term is in the positive x direction. That's different from normal. Okay? So, you can go about this a couple different ways. I think you need, and at this stage of your physics journey, I think you really need to understand why these two are switching, okay? Last year I told you it's enough to remember that for ramps, cosine and sine switch. Now you really need to understand why they're switching. One other way to remember it is to remember where the angle goes. The angle, theta, that you got from up here, it's the same angle as is up here. This angle, theta, it always goes between the force of gravity and the component that is perpendicular to the ramp surface. Here's the ramp surface right here because the normal force is perpendicular to that. Here's the component of the force of gravity that is perpendicular to the ramp surface. And so the angle here between FG and the component that's perpendicular to the surface, this must be theta right in here. And that helps you determine which is sine, or which is cosine and which is sine. Now I've spent about 4 or 5 minutes explaining this because I wanted to walk you guys through it. As you go, this gets much, much quicker. You should be able to do this within 20-30 seconds as you get more and more practice with this. What we're going to do now is write out the net force equations. Let's start in the x direction, or let's start in the y direction actually. We have in the positive y direction Fn minus Fg cosine theta. Notice I'm not writing Fg because that's not in the y direction, that's in an in-between direction. Fg cosine theta is strictly in the y direction. That's the component of Fg that's in the y direction, so we want to use that. Minus Fg cosine theta equals, because it's F net in the y direction, m ay. We already talked about how this object is not just going to blast off the ramp surface or sink down into it. That means it's not accelerating in the y direction. This must be 0. It's not moving in the y direction right now, and it's not going to start, so that must be 0. So what I'm left with is Fn equals, I bring this to the other side, Fg we know is really mg, the force of gravity is equal to m times g. Fn equals mg cosine of theta. Not particularly interesting by itself, but if you think about it, a lot of times we have the result that Fn equals mg, or Fn equals fg. That's not the case here. Don't fall into the trap where you think that the normal force is always going to be equal to the force of gravity, because here it's very clearly not. What about the x direction? Well, there's only one force in the x direction. That would be Fg sine theta equals max. But again, Fg is really mg. So look what I have on both sides here. I have an m. If I were to divide both sides by m, they cancel out. And what I'm left with is ax equals g sine theta, which is a very, very interesting result, and I'll show you why in just a little bit. First, let's practice just plugging into that equation, though. What is the acceleration in the box down the ramp if the ramp angle is 25 degrees? Well, since ax equals g sine theta, we're using, in this class, g is 10 meters per second squared times the sine of 25 degrees. 25 sine times 10. That's 4.23 meters per second squared. Okay? And we can actually test, and we will test that in class, and we'll prove it. Now we get to the interesting part. How would the acceleration change if a box that was twice as massive is used instead? Well, let's think about the equation. The acceleration is ax equals g sine theta. Which one of those terms represents the mass? None of them. G does not represent the mass, it's acceleration due to gravity. Theta is just the angle, and sine is just an operation. So the answer is, if you change the mass, nothing changes. It wouldn't change. The acceleration stays the same. It wouldn't change. Since there is no m in the equation for the acceleration. Now, you might say, wait a second. I know the net force equation is F net equals ma, and that mass changed. So how come the acceleration didn't change? Well, think about it. If that mass, you were correct that that mass changed here, and that should mean that now the object has more inertia and it's harder to accelerate. But the force that was bringing the box down the ramp in the first place was a component of the force of gravity, Fg sine theta. So it is true that the mass increased, and therefore the box has more inertia and is harder to get moving, but the force that is moving the box also changed. The force got bigger. So even though the mass doubled to 2m, the force of gravity doubled as well. And that was what ultimately drove it down the ramp. So these factors kind of cancel each other out. Okay? So that's a very simple picture. It's probably about as simple as you can get with ramps. Notice that even though the box moved down the ramp, there's no applied force or anything here. It didn't say anything about anyone pushing it down the ramp. It moved down the ramp because of a component of the force of gravity. When we come back, we'll look at a slightly more difficult example.